Okay, here we go. Last 20 questions of the 2012 PAT. Question numeric response number 3. We've got a graph, toxicity for chemical X, and we've got the deaths per 100 test subjects on the left and the dosage over here on the right. It says to the nearest milligram per kilogram, because that's what the dosage is measured in, milligrams per kilogram. So every kilogram contains this many milligrams of this substance. So to the nearest milligram per kilogram, the LD50 value for the chemical X is. So if we're saying that this is deaths per 100, 50% of 100 would be 50. So we're looking at, because remember LD50 is the dosage that would cause 50% of test subjects to die. So we've got 50%. That reads down to 100 milligrams per kilogram would be that LD50 measurement, that the toxicity that causes half of the population to die. Okay, so our answer would be 100 milligrams per kilogram. Okay, next, here we go into the electrical unit. A student is asked to explain the relationship between current, voltage, and resistance using a hydroflow model as shown below. The water in the model could be used to represent electrons. So also in this model, the amount of water in here, or the level of this water, would represent our voltage, like the potential, and then the water stream and how fast it's flowing, that would be like our current. Also, this opening, the size of this opening, would represent resistance. If I have a small opening, that's a high resistance, and we would get low water flow. If I had a big hole in this bottle, the water would empty very fast, and that would be like a low resistance, right? So low resistance has a lot of water, is going to flow very quickly. But they just asked us, what does the water represent? And the water would represent our electrons, because that's what is moving around and flowing around in an electrical circuit. Okay, next question. Here's a circuit. We can see electrical circuit of a garage. The component, and it says the component that is protected by the circuit breaker when both switches are closed is the... Okay, here I have the switch is closed, the switch is closed, so that means we've got electricity can flow. So we've got our power source, electricity can flow through here, through my exhaust fan. It can flow through here, through this heater, through this light, back to my power source. It can also flow here through my furnace motor, through this circuit breaker and back. So a circuit breaker, remember, is like a switch that can open when it senses a temperature. Let me just get there, move this microphone. So it will so it will open when it senses a temperature that is when it senses a current that is too high. And a high current, if there's too much current running through here, it can burn out this motor. So if it senses a high current, it opens up like a switch does. And when it opens up, this circuit breaker here, and here's our circuit breaker. If that opens up, then electricity stops flowing. And so if the electricity stops flowing through this, that means we're protecting that furnace motor. Okay, next question. Which of the following electrode and electrolyte combinations could transfer electrons when connected in a circuit? So we cannot have two copper electrodes. If they're the same metal, that's no good. So zinc and copper, that's good. It's going to be either A or C. And we have the options of salt water or distilled water. So we need an electrolyte solution. Distilled water does not have any electrolyte in it, it's just pure water. Our salt water is going to going to be an ionic solution, and that is important to have our battery work. So our answer is A. Next question. 34, we have a diagram above here, electrical circuit. It says if the light bulb at position 6 burns out while the switch at position 2 is closed, then so let's just look at it. So switch is closed, okay, and it says if the light bulb at 6 burns out. Okay, so that's open. It gives us some options here. It says A, the light bulb at position 7 will dim and the motor will spin more slowly. So where are we? Light bulb at 7 will dim and the motor will spin more slowly. Well, so if this light bulb here is out, we're still going to have electricity flowing through here. And it's not really going to affect the light bulb. It shouldn't change or dim because it still has the same amount of voltage dropping across it because it's a parallel circuit. So it's not going to dim. It's got the same amount of voltage going from here to here and here to here. So that shouldn't really change. Remaining 2 light bulbs will turn off and the motor will cease to spin. Remaining 2 light bulbs will turn off. If this one empties, it's saying that this will turn off, this will turn off. Definitely not the case, right? We still have a pathway for electricity to flow. It's no longer flowing through here. However, it can still flow through here and it can still flow through here. So this is definitely incorrect when it says that the light bulbs will turn off. A light bulb at position 7 will brighten and the motor will spin more quickly. So that's trying to tell us that we're going to have more electricity flowing through this motor and this light. And that's not really the case again either. Just because this light bulb went out doesn't change the amount of voltage going across these. So that's not correct. And again, if you're not totally certain of these, that's okay. You can just go until you find one that definitely is correct and makes sense. Let's look at this one. It says the remaining 2 light bulbs will remain lit and the motor will continue to spin. So whether you're uncertain as to whether the lights would dim or get brighter or anything like that, just check all your answers. And if you find one, so what did we say? This light's out. And the last one just says the remaining 2 lights will stay lit and the motor will continue to spin. That's a simple enough answer to verify whether they spin faster or not or get brighter or not. There's still electricity flowing through here. There's still electricity flowing through here. So these lights will still both be on and this motor will continue to run. So answer is D. Question 35. The reason that static electricity cannot run an electrical device is because the static electricity cannot supply a continuous flow of electrons. It can discharge quickly, like a lightning bolt or a spark from a sweater, but it's a very instantaneous, and as soon as that charge transfers, that's it. There's no continuous flow of electrons. So all these other answers don't really make sense about not providing enough current. In fact, lightning is this form of a discharge from static electricity, and it has massive currents, but it's just momentary. That's the only problem. Does not provide enough voltage. Again, same thing. You could think about lightning, and there's plenty of potential there, but it just is temporary. And then B said cannot flow through the device's conductors. That's also not true. If you had a static charge on a shirt and you put a metal rod there and you see a spark, those electrons are going into that conductor, And if you had it like a circuit somehow closed, it would flow, but just momentarily. That's the whole main part. They cannot have a continuous flow of electrons. Okay, next. List the devices shown above from the least efficient to the most efficient. Okay, we've done questions like this already. So I'm not going to go through it all. We'd do the calculations. This one we would have 79 over 675. Calculate that. This one would be, well, 9 over 9. That's 100% efficiency. So that's obviously the highest one. And there it is, most efficient. Here, 3 over 13. Calculate that as a percent. And 0.031 divided by 0.781. And when you calculate those efficiencies, you should get this number. Okay, don't need to go through the details. It's just more explaining how the question is done. So as long as you understand that, you should be good. Next, how much energy consumed in Canada in 2006 was provided by fossil fuels? So this is total energy consumption. So it's just a matter of knowing which ones are fossil fuels. Pretty easy question. Gas, oil, coal, hydroelectric, nuclear, and other renewables are not included. So fossil fuels are these. We just add them up and we would get 66%. Okay, next. Now we didn't talk a lot about this, so I'll explain this question the best I can here for you now. When the south pole of a magnet is moved into the coil of wire, current flows, and there is a reading on the galvanometer. Just think of it like a measuring, like an ammeter. Okay, it's measuring like the current flow. Okay, so which of the following changes would not increase the reading of the galvanometer? So what's happening is when we have a coiled wire and we move an electric field through it, so we have this, a magnet has when we move a magnetic field in it. Without getting into the details, when we have a coiled wire, we have a magnetic field that changes inside in that coil. It induces a current in the wire, so we get a current flowing in this wire. Okay, so that's what you need to know. And also, the faster we move that, the faster we change that magnetic field, the more current, the stronger current we get. Another thing to know about that is if the magnetic field is stronger, if it's a stronger magnet, that again produces a stronger current in the wire. Okay, so by moving magnets through coiled wires, we can produce a flow of electrons. So we're essentially producing electricity, and that's exactly how generators work. But we don't need to get into the full details of that. So let's look at our options here. We said, which of the following would not increase the reading on the meter? So moving the magnet faster in the coil would make a higher reading. Wrapping more wire around the coil would also, so I didn't mention that one, but if you only have a few coils and then you move the magnetic field, it's going to get some current. Okay, but if we have more coils wrapped, that is going to also cause more current to flow. Okay, because more of that wire is getting affected by that magnetic field. So that's another one. Using a stronger magnet, that will also result in more electron flow. But see, reversing the poles of the magnet, it doesn't really matter. If we reverse the poles, the current will flow in a different direction. If it's measured in this direction, instead it will measure in that direction, but it won't change the intensity of it. So reversing the poles of the magnet doesn't matter. So if I flip this magnet around, so that's south pole and north pole, and then started moving that magnet back and forth in here, or moving it through there, however it is, even if I just move it in one direction quickly, we'll get a reading. So yeah, reversing the poles will not change, will not increase the reading. It might change the direction the current flows, but it won't increase how much current flows there. Okay, the power rating of Alex's flashlight is 4.5 watts, and he uses it for 60 seconds. Knowing these values, Alex can use the energy formula to calculate the amount of energy used by his flashlight. So energy, we said, is equal to power times time, and that's power in watts, and time in seconds. And that gives us an answer that is in joules. Energy is measured in joules. So we have 4.5 watts times 60 seconds, and we get 270 joules. Okay, next question. The resistance of a wire can be reduced by doing either decreasing or increasing the diameter of the wire, or by decreasing or increasing the length of the wire. Okay, again, something we didn't really get to talk about, but it's a pretty easy concept actually. So think about this water bottle situation we saw a second ago. We got our water. This could be like our electrons. If I have a little hole, a little bit of water gets out. Oops. If I have a large hole, more water can flow. So we would have a higher flow of electrons and a higher current. So remember, the size of this hole represents the resistance. If it has a larger opening, there's less resistance and more water can come out. If it has a small hole, there's more resistance and less water can come out. So the same actually applies to electrical conductors. So if I have a wire, and think of it like a little cylinder, it's a skinny wire made of copper, and it looks like this. A smaller diameter only is going to restrict electron flow the same way that water would. If I have a thicker wire, that is going to allow electrons to move more freely. So this provides less resistance to electron flow. So a larger conductor with a wider diameter has less resistance because it allows electrons to flow. Okay, so the first part of that is so the resistance can be reduced by increasing, could be one of these two, the diameter, so the opening, right? The diameter of this opening on my conductor, of the wire, or by either decreasing or increasing the length. So every metal or conductor has a certain amount of resistance. With a good conductor like copper, there's a low amount of resistance, okay? But the more metal you have here, the longer it has to go through. Those electrons do encounter some amount of resistance, not a lot, but there is some resistance in there. If I have longer wire, those electrons have to travel, think about it this way, through more of that copper or more of that metal to get where they're going. So that can increase the losses in this wire. But anyway, there's more resistance because there's just more of a tunnel to get through. So the second one is we can reduce the resistance by having increasing diameter, a bigger wire, or by decreasing the length. So wider means less resistance, and shorter also means less resistance. Okay, so the worst situation would be to have a skinny wire going a long distance. That would be a high resistance. If I have a wire with a bigger diameter and it travels a shorter distance, this would be the lowest resistance. Okay, question 40. In order for a thermocouple to function properly, which energy transformation must occur? Um, so a thermocouple is a device that measures temperature, and well, it can activate certain things. So in like a vehicle, for example, you might have a thermocouple, and it's the device that senses the temperature of, it can say the temperature of your engine, for example, and then it sends an electrical signal to a circuit which can do things like turn on a fan, which can start to spin and blow in the radiator of your car and keep your engine cool from air movement. Okay, so here we have heat being sensed by this thermocouple. A thermocouple, what it does is it takes heat energy and it converts it into an electrical signal. Okay, so travels. So, oops, I'm on the wrong question here. So, for a thermocouple to function properly, we have thermal energy is converted to electrical energy. Okay, that's just how those work. All right, so that's enough electrical stuff. On to question 41. Talking about space now. Okay, so space junk can potentially damage spacecraft or the space station because space junk reflects cosmic rays, produces a lot of heat, produces attractive forces, or travels at high speeds. It's because it travels at high speeds. They don't reflect cosmic rays, doesn't produce heat, it's just junk floating in space and producing attractive forces. No, I mean, it's not, these are small bits of things. They don't have gravitational forces or anything. So it's just because they're traveling at high speed. They're flying around out there. Different satellites and different things have different orbits. So things are traveling at different speeds out in outer space. So imagine you're out here in Earth and you're out here one day in your spacesuit fixing your spacecraft, and there was a satellite that was launched into orbit, and now it's uh, still out there floating around. But if you're only traveling at this velocity and this satellite was orbiting much faster for whatever reason, there's a space junk, it's coming towards you with a high speed. It can cause damage, right? So if there's junk out there in space, decommissioned or broken down pieces of space junk or things from a launch of a rocket, maybe a piece of a ship that came off, any of that stuff could potentially be moving at a high speed compared to your current speed and cause damage. In 2006, scientists predicted the years when comets would approach Earth based on approximate lengths of their orbits, which were calculated in years. So here's our sun, and then comets, right, have an orbit. And here we are going around the sun. Here's Earth. So we might get to see this comet when it comes close to us, close to the sun. So the number of years when comets would approach Earth or get close to Earth. So there are the 4 different comets they're talking about, and here's the year of close approach to Earth, 2007, 8, 10, and then here's the next year. So if we look at 2008, the next one's this comet's going to return again after, let's see, 7, so 15 years. 2007 to 215, once it comes by, it'll come back again in another 8 years. 2008 to 2015, that's going to return in another 7 years. And this comet Mueller 4 will return again after 9 years. So it asks, according to the information shown above, which comet has the smallest orbit around the sun? Well, if it takes longer for it to return, that's because it has a longer orbit, right? If it has a longer orbit, it's going to take longer to return. So the smallest orbit would be the one that comes back to Earth a lot sooner. And the one that comes back to the soonest is only takes 7 years to come back after the last time it was here. So it would be this comet here. Space shuttles are propelled into space by rocket fuel, chemical propulsion. Ion propulsion, nope, that does not have enough force. That's used in once rockets are in outer or things are in outer space. Solar propulsion, again, like wind, solar sails provide some amount of thrust, but not nearly enough. That's more useful once in outer space. Nuclear propulsion, I do not think there's even such a thing. Nothing that I know of, but chemical propulsion, yes, correct answer. Statement 1, 2, and 3. Humans should send animals into space to test the effects of zero gravity. Statement 2, there are no regulations regarding military uses of space. And 3, dead satellites and other space junk litter Earth's orbit. Match each of the statements above with the type of issue to which it refers. So the easiest one to pick out is probably the environmental one right away. So they're dead satellites and other space junk will litter Earth's orbit. That sounds like something that's environmentally motivated comment. Worried about the mess it's going to make. So that one we can get rid of now. And then ethical, and then political. So ethical is like whether something is right or okay to do. Humans should send animals into space to test effects of different gravity. So this could be an ethical question. Is it ethical to send animals up there for those tests? And that leaves us with the last one being the political statement. There are no regulations regarding military uses of space. So things to do with regulations, and militaries and stuff like that would definitely be like governmental things. So like political issue. Okay, four students conduct an experiment to determine which scenario will provide the best estimate of the distance to a flagpole. So we've got these two students standing further apart, 20 meters apart, and they're going to use this method of triangulation, right? They're going to try to measure an angle from here to here, and that's going to help them to calculate this distance. These guys are also going to measure two angles and to try to calculate that distance. So the most important thing here in triangulation is the wider we can get this separation of these 2 points, the better it's going to be. Because if you're very, very close together, this angle is less likely to be accurate. So yeah, if we've got, so if I'm standing even closer together, I have if I move just a little bit, or if I'm not lined up quite properly, that can create a lot of errors. So hopefully we just can kind of recall this from what we talked about in class, but it's important for it to have a wider. Okay, so that's always going to be better. Without getting into details right now as to why or how to explain that, it's just remember for now that the wider is better. So it's the baseline length that is going to. So that baseline is talking about this distance between these two people. That's going to give a more accurate measurement of those angles, and then therefore giving us the correct calculation of this distance. Okay, an unknown gaseous planet has a radius of 24,000 and some odd kilometers, a period of rotation of 0.67 Earth days. So that means it spins around once in less than one Earth day. So it spins faster, right? and a period of revolution of 60,190 Earth days. So period of revolution meaning how long it takes to go all the way around the sun. So here's some other ones to consider. So Earth, the radius is 6,000. That's the radius of the planet, right? And this is some unknown gaseous planet. This is its radius and its period of rotation. And so period of rotation is how fast. So let's look at Earth. Earth spins around once in a day, right? It turns around completely one time. Period of revolution is the number of days it takes to get around the sun. Okay, and the planet composition terrestrial. Okay, great. Mars, for example, it's a smaller planet. It spins around a little bit slower than Earth. It takes a little bit more than a day to turn around completely. And it travels around the sun once in, not quite twice, but almost twice as long as Earth. So it takes much longer to get around the sun. All right, so you get the idea. Let's look at the question now here. The unknown planet would be found, and they're saying either inside Earth's orbit, outside Uranus's orbit, between Earth and Mars, or between Saturn and Uranus. So how would we know that? Let's look at what we have. We know the radius of the planet. That can give us some idea, because remember, the larger planets are further into the solar system, but it doesn't mean they're all like exactly going from smallest to largest. Okay. So I wouldn't rely on that, but let's look at what else do we have. It says the period of rotation is 0.67 days. Well, again, we've got, let's see, Mars. We have Earth is the third planet from the sun. Mars is the fourth one. So here Earth is spinning around once a day, and then further out Mars is spinning a little bit slower. And then further out to where Saturn is, it's spinning faster because it only takes less than half a day to spin around. So that doesn't really tell us exactly where that's sitting. That's not really going to help us know exactly where that planet is. But what about period of revolution? Okay, just like the comet problem. Here's the sun. If we're closer to the sun, we have a smaller orbit. The further away we get, we have a larger orbit. So our period of revolution is going to be bigger. That's going to be the more reliable factor. And here we can see the Earth has a smaller period of revolution, and Mars is bigger. That makes sense. It's the next planet. Saturn is bigger, and Uranus is the biggest of these. So that's saying that Uranus is the furthest out. It's taking longer for it to go around the sun. Much longer. So this unknown planet has a revolution of 60,000 days. So that's going to be even bigger. It's going to be outside of the orbit of Uranus. So answer to that one is B. So, and we can see that there's that pattern, right? That these are increasing here as we go outwards. Whereas the spin doesn't really follow a pattern. Some are spinning faster and slower. It doesn't really relate to their orbit. And same with the radius of them. The radius of the planet does not follow a pattern, but the period of revolution does. And that's because of these orbits being bigger and bigger. All right, next question. Which star is located at an altitude of approximately 40 degrees and an azimuth of 40 degrees? So remember, azimuth, so here's north. Azimuth, this would be 0. This would be 90. So if we're measuring from 0 to 90, where 45 is about halfway, and 40 would be about here. So if we follow that, okay, maybe we're not getting our angles exactly right, but we're looking at this direction. So we're talking about somewhere on this half. Okay, we're looking in this direction. Now, just based on the altitude, we're either looking at this one or we're looking at this star here. So 40 degrees, remember, this would be 90 degrees all the way up to the top if we're looking at for altitude, and this would be 0 degrees as far as altitude goes. So the higher we go, the higher the number. For me, 45 is about in the middle, right? Would be about 45 degrees. So less than 45 degrees would be here. So I would say that this is our 40 degrees. This one up here could be, I don't know, maybe 60 degrees. It's something higher than 45. So we're looking at this direction. Okay, so we're looking at, that's the 40, that's our 40 degrees of azimuth, right? And then this way, from once we've determined which direction we're pointing, which is this way, that's our 40 degrees from north. Then we look, how high up are we? And then, so 40 degrees would point us here at Z. Okay, next one. Use the following information to answer these questions. To the next question. Which of the diagrams above represents Aristotle's geocentric model? Okay, geocentric means Earth in the middle. So that has sun in the middle, that has sun in the middle. Here are these two. So the geocentric model is saying everything goes around the Earth. So here's the moon going around and the sun going around. In this case, the moon and sun are going around, but that's not the geocentric model. They wouldn't explain why the moon moves through the sky, right, so quickly. Anyway, the geocentric model is everything is centered around the Earth, right? So including the moon and the sun. So answer to that would be 4. 48. Which of the following devices could be used to prove the presence of helium in the sun's atmosphere? So we talked about this in the last test. Remember that one? It was like the colored band was multiple colors, and then we had these dark bars, and that was the spectrometer, or right, the spectroscope, and that is helping us determine the composition of something, composition, which means what it's made up of, what it's composed of. So what are the elements that are in that thing? And helium being one of those potential elements. So which of the following devices could be used to prove the presence of helium? That would be the spectroscope. Okay, radio telescope can see images and stuff, but it can't tell the composition of the elements. Space probe, well, that's just something that's out in outer space. It could have all kinds of instruments on it, but that alone doesn't tell us enough. And a satellite, which is orbiting around Earth, again, same thing. So it's the spectroscope is a piece of equipment that can help us determine what things are made of. Almost there. An advantage of the optical telescope over radio telescope is that optical telescopes can be used. Right answer is A, to produce clearer images of celestial objects. So to observe, let's look at the other option. So it says they can be used to observe a greater portion of the sky. This is not correct. Radio telescopes can see much more, much further, and so on. They can also see when there's cloud cover, and they can also see during the day or night because they're not using visible light. But optical telescopes can produce much clearer images of celestial objects. And 50, a vast collection of stars held together by gravitational attraction is called a galaxy. Here's one you might get tricked by. You might want to think constellation because you're thinking, oh, look at, I know constellations, they're like together, but they're not held together. When we look up the night sky, we see these stars as if they're clustered together, but in reality, here's the Earth. Those stars that we see could be at very different distances. They're not even close together necessarily. But when we look at them, right, from this perspective, they appear to our eye to be all at the same spot. So we would see them lining up, clustered together, when that's just what we see, right? That's our perspective. But when in reality, they're all at different distances and places. So they're not held together by gravity. They're way, way far apart from each other out in the universe. So it's not a constellation for sure. Now the solar system is not a collection of stars. There are planets, and they are held together by the gravity of the sun, but that's not a collection of stars. And a nebula, well, that's just that's before a galaxy forms. It's cosmic dust and stuff. It is held together by gravity, but there's not even a star being formed yet. Remember, the nebulas are the birthplaces of stars. So a galaxy, however, is a collection of stars held together by attractive force, a gravitational attraction, and we can think about the Milky Way, right? A spiral galaxy is composed of many stars, and they're all kind of held together by a central force of gravity, and our solar system is somewhere here, and our planets are somewhere here. But this is a great big collection of stars and planet systems. But yeah, so we would answer to that one is galaxy. Okay, and that is it. So I think this is gonna probably do it for videos for the PATs. If I have time tomorrow night, I can post some more, but that's night before the exam. So hopefully this gives you guys enough to work on. We'll see what happens tomorrow. If there's some time, I'll add some more questions, but for now, this is what we're going to have as far as video explanations.